super out of the ordinary for like someone like a family and stuff at home and a child.
Yeah.
Like so most people like I forgot his what was his name? Yeah, Bo. Most people like Bo in this situation as a teacher would take a long time, but just slowly chipping on that.
Right, right.
Professor.
Yeah.
Just to estimate, how many units do you think we could catch up by today? Like, how much information do we have left after this class is over?
2
Two?
or 3, depending if you count.
Oh.
I count exponentials and logarithms as 1, but
Professor,
if you count that as 2, that's 2, and then like conic sections. So
I'm going to need to leave 15 minutes earlier today.
cool.
Sorry about that.
All right, so I was able to squeeze in what I wanted to last time, which was vectors and then the dot product at the end. So this lesson is called matrices. There's a little bit here, probably new for many of us, but if you have some computer science and background knowledge, it might be a little intuitive. But anyways, this is our final lesson on next week's exam. So I'll tell you exactly what topics are on it, and then yeah, we have class on Tuesday, which we will go over exponentials and logarithms, and then one final section called conic sections, just trying to decide how I'm going to get that to you. So more on that later. But yeah, matrices. Anyone know what a matrix is? A movie. Anyone see that movie? No? Really? Wow, that's a good movie. That's part of your homework. No, it's really not, but watch what a matrix. Watch the matrix. Wow. Anyone know what a mathematical matrix is?
Can I ask, what is a matrix?
Yeah, that's what I'm asking. That's what I'm asking to see. I'm getting a vibe that no one knows. All right, so we're getting there. All right, then since no one knows, we'll start with a puzzle. Maybe not a puzzle, but all right, so suppose these are like 3 cities, 3 destinations, and there's 3 highways from city 1 to city 2, and 4 highways connecting city 2 to city 3. So how many ways could one travel from city 1 to city 3?
12 ways.
12. Claim of 12. You say 12? 7?
I think it's 12 too.
You think it's 12 as well? I think it's 7. Who else? We have 3 votes for 12, 2 votes for 7. Zero votes for nothing for silence. Actually, 1, 2, 3, 4, 5. 8 votes for silence. How do you know it's, or why do you think it's 12?
Because since there's 3 highways, like if you look at this example, like say for instance, instead of 4 highways on the second rotary, there's 1. There's 4 possible there's 3 possible ways that city 1 could travel to city 3 if there's 1 highway instead of 4 highways for second route. So if you multiply that by 4, that's 12. So that's all I got as well. Just common sense kind of. I mean, I think it's sort of like what.
If it's common sense, everyone would scream 12 right off the bat. So I don't think it's common sense.
I count.
You counted them?
Yeah.
All right, help me count them. So I'm not there yet. So I have one choice, or kind of do the same original path. That would be a different choice. So 2, your same original path. 3, same original path. 4. So there's 4. So that's taking this highway, and then from here I have 4 choices. But I think we can also see if I went the middle highway, then I'd have an additional choice, or again, or again, or again. So that's a total of 8. Oh man, it's not 7. And then this final road, 1, 2, 3, 4. And there they are, 12 choices. Cool. So I don't know if it's common sense, but
I mean, if you go algebra.
how is that algebra? I'm curious.
Well, if you want me more specific,
It's not algebra. It's actually a branch of mathematics called combinatorics. So it's not algebra. Combinatorics, the way of counting.
Each instance that you have a possibility, you take a number of options you have, and you multiply it times the number of options each other set of possibilities.
Is that always true?
As long as you don't have to account for things like exclusions or other variables.
As long as the events are independent, we would say. But
Yeah.
take a probability or course or class in, as I said, combinatorics, which is literally how to count, or discrete math, all of those. But I would definitely not call this algebra. How many paths from 1 to city 3?
We're 1 to 4, you said? 1 to 3.
Yeah. Is it 14? Okay, I'm not gonna try that one.
No, now it's theoretically infinite.
Theoretically, it's a lot harder. But I'm pretty sure every day we can find flight paths in this country that would exceed this by a lot. And so coding this information and being able to work with it so that we could figure out how many paths are available between cities no longer is an easy task. And so now I've driven a need for something. I've driven the need for a mathematical tool called a matrix.
So is it an equation to help solve complicated problems? Or something else? Okay.
So a matrix is, at the end of the day, a rectangular organization of information. For example, we could count, let me just get one thing right here. I'm actually going to use this diagram. Did I go too much with it? Yeah, that's all right. We'll use it on the fly. We're going to count all the paths here. We're going to organize all the paths here. We could count, let me rephrase that, organize all the paths as follows. You know what I want to do? Let's see if I can do this. Oh, sweet. Perfect. So we're going to count the number of paths starting from City 1 and back to City 1. How many? How many highways or paths or airplanes, flights, start at City 1 and return to City 1? 1. Right here. You can start at City 1 and come back to City 1. How many paths from City 1 to City 2?
3.
Right here, 1 to 2. How many paths from 1 directly to 3? And from 1 directly to 4?
0.
Cool. From City 2 to City 1? 2 to 2? 2 to 3?
4.
Oh, I missed it too. 4. Yeah, there we go. And 2 to 4.
1.
There we go. 3 to 1?
0.
3 to 2?
2.
3 to 3?
0.
3 to 4? 4 to 1? 4 to 2?
0.
Here you go. 4 to 3? And 4 to 4? There we go. We might call this, actually, I'll just call it A. And in a matrix form, we would write this. Boom. And so we're looking at our first matrix. It's literally a rectangular array of information. We typically use capital letters for matrices. And I'll go a little more in detail in a minute, but that's it. This is what a matrix is. We put all the information between 2 big, large square brackets or whatever size we need. And that's that. So last time you said, or we talked about a poor village that was attacked by an earthquake. Does it make sense to multiply this? Is there any context in this situation then?
There could be.
What would it be? What would this represent?
It could represent 2 Earths, like basically a mirror version of another Earth or planet.
Okay. A different planet, so another copy of this. What else might it mean?
Maybe you double all the values.
Can you build on that a little bit more?
Well, from the rectangular, for example, instead of like if you were to, I was talking about the chart, not exactly.
Okay, so yeah,
I guess
maybe
from there you could,
it means to just double all the values inside.
like,
What would that mean in this picture? Yeah, it would double all the paths. So 2 would just mean, hey, everything got doubled. We're gonna do another one here, 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 this way, that way, that way, that way, that way. One more here and one more there. It's exactly what it means. And it's exactly what we would see here. 2, 6, 0, 0, 0, 0, 4 becomes 8. Save myself. 0, 4, 0, 0, and 2, 0, 0, 0. Not matrix multiplication, just like not a vector times a vector, but this is called scalar multiplication. Very similar. Already, a matrix is somewhat acting like a vector. All right. I think I'm going to pause with my little hook for what a matrix is and maybe doing something with it and just go a little more formal. So, to be clear, a matrix is rows by columns of numbers arranged in brackets. This has how many rows? 2. How many columns? So we say the dimensions or the order is 2 by 3. 2 rows, 3 columns. 2 by 3. Eventually tonight, we're going to multiply matrices. And for that to work, the first thing we need to do is check the orders because, well, we'll see in a minute, or when we get there, not a minute, but it's potential that it can't be done. We're going to multiply 2 matrices if possible, but there's a chance it won't be possible. Something has to be in agreement, and it just comes from checking rows by columns. But if you mess up your columns and rows, which I did when I remember being in whatever first time I did it, I didn't think it was that big of a deal. I don't know why I didn't, but I was like, oh, just whatever. Has to be that structure. As I said, capital letters are typically used. Matrix. Let's try that again. Where? Oh, frick. So if we use a capital letter for matrix A, then there are going to be some objects inside of it, some numbers inside of it. And if we want to specifically talk about, for whatever reason, let me just give an example. Like if I specifically want to talk about this, then I would say this is lowercase a, because I call this capital A. I would call this lowercase a 1, 2, 3, 2. I would subscript it as A 3, 2. Represent the third row, second position, second column position. A square matrix is exactly what you think it is. And now all the, I guess, vocab and notation stuff is out of the way. Pretty simple, just make sure we're all there. Here's an example that assesses our vocab. What is the order of this matrix A? We'll identify lowercase a sub 1, 2 and lowercase a 3, 1. So what's the order?
You say 3 by 2?
We would say 3 by 2, 100%. So just reminding us, you count this, 3, count these, 2. So answer is 3 by 2. What is the number represented by that notation? -2. We go to row 1 and position 2, -2. How about A sub 3, 1? 1. So you go to row 3 and position 1.
Oh, so it could just be A3.
What's up?
It couldn't just be A3.
No,
Okay.
because you're in the third row, but you need to say what position you're in. All right. So we motivated with like the highways, the need for what a matrix is. So counting the paths, simple cases, but for organizing a lot of information, a matrix could potentially be very helpful there. We haven't kind of answered any more questions. I just kind of let that go. So if you're like, oh, that was abrupt, and we didn't actually count the paths, still got work to do, but I motivated the intro. But now officially vocab out of the way, assessing the vocab, adding and subtracting. To add two matrices, first and foremost, the orders must be the same. And then it's completely positional. We just add the two positions together. So take this, take that, and literally add them together. -1. Take row 1, column 2, take row 1, column 2, 0 plus 4 is 4. This would be -2, this would be 0, this would be 10, -2, 1, and 7. Subtracting exactly the same thing, have to have the same order, and we just perform the operation. So pretty simple. -2 minus 1 would be -3. 4 minus 0 would be 4. -1 minus -1 is 0. And -5 minus 5 would be -10. So just make sure you get the right order. Obviously with subtraction, 8 minus 2 is 6. 1 minus -3 is 4. -7 minus 8, -15. And 1 minus 6 is -5. Scalar multiplication, I did show that briefly. But to kind of just put it nice and clean. This was motivated in the opener. If we think of these as to and from diagrams, just imagine that. Doubling it as was said in class would just mean we're kind of doubling all the paths, the highways. And so we can multiply by any number we want. A half, -1. I'm not going to drag it on. But a more common question might be if A is -4310 and B was I'll give you a minute. Putting together addition, subtraction, and scalar multiplication. It's pretty simple. In case anyone's like fell off the bus past 10 minutes, you're going to A, smack all of these with ×3. That's going to be 3A. Go to B, smack all of those with ×2. And then since they're the same dimension, simply add the results. Okay. What was in row 1, column 1?
Negative 14.
Correct. Row 1, column 2.
Negative 1.
Then row 2, column 1.
25.
And last position.
10.
Boom. Anyone else get that? Cool. All right. Onwards we go. Matrix multiplication. So not scalar multiplication, but literally one matrix times another. And I said something in the motivation with those paths, like, well, scalar multiplication felt a lot like vector, like 2 earthquakes, 2 flight paths, or I call them flight paths, but I said highways in class, but I always think flight paths. Well, let's just see where I'm going with this. Bottom line here, must have So just going to do it with the concrete example. We must have this be true. So the columns of your first matrix must be in agreement with the rows of your second matrix. The number of, this is rows, columns, rows, columns. So this is a matrix, and this is a different matrix. As long as the column values of the first match the row value of the second, then you can multiply 2 matrices. Furthermore, the solution dimensions, the solution's orders, is going to be a 2 by 4. So immediately, is matrix multiplication commutative? Can we switch the order? Definitely not. A matrix times another matrix is not, you can't just switch the order. Order matters. That is crazy. One of the first times in math, multiplication is not commutative. Can't switch the order. Prove right here. If we put 4 up, it would say 3 times 4, but that doesn't match the 2. So order matters, and knowing how to read columns and rows is important. We'll start with this. The most common type of matrix multiplication is a 2 by 2 by 2 by 2, so 2 square, but it's just the most common. But in the homework, you're going to have a variety. So suppose matrix A was a 2 by 2 with these 4 elements. Matrix B is another 2 by 2. These are in agreement. Our solution will be another 2 by 2. So in a minute, I'll tell you what we're going to write here, but this is the solution in row 1, column 1. That's this position. This is row 1, column 2, and so on and so on. And I say that because it's literally what we're going to do up here. We're going to take row 1 and the values in column 1 and basically find their dot product. If you remember what the dot product was, it was horizontal positions plus vertical positions. So similarly, it's this position plus that position, AE plus BG. To find in our solution, row 1, we go back to AB, and then we do the same kind of algorithm or dot product. Really, that's what it is here. AF plus BH. A times F, B times H. In this position, the solution that's in row 2, column 1, that's later here, you go to row 2, you take column 1, find its dot product. So anyone feeling brave? Plus? Yep. CE plus DG. Somebody else?
CF
Yep.
plus DH.
All right, that's at least 2 of us. And maybe, hopefully more of us. We'll find out in a minute. CF plus DH. So I'll just kind of act it out for us. So again, go to row 2, go to this column 1, and find their dot products kind of as you slide along. Go row 2, boom. Go GH, find their dot products as you move along. Let's find this product with actual number values. So again, I find it helpful to go through. You don't need to do this if you can. Some people see it a lot faster than others. But since I'm teaching to everyone, it's a good strategy as you're getting going. This is 2 by 2, that's 2 by 2. Obviously, our solution is going to be a 2 by 2 because we just did a more abstract example. But take now, set up your solution, and then write what each position is. This is row 1, column 1. This is row 2, column 2. This is row 2, column 1, and so on and so on. And that reminds you now, go back to your matrices, take row 1, take column 1, and find the dot product, which just means multiply, add, multiply, add. And in a minute, we're going to extend this beyond a 2 by 2. You just keep multiplying and adding, multiplying, adding, multiplying, adding. But we'll come back to that, right? So row 1 is 1, 3. Column 1 is 4, 1. 1 times 4 is 4. 3 times 1 is 3. 4 plus 3 is 7. 1 times 4 plus 3 times 1, 7. Row 1, column 2. 1 times 6 plus 3 times 0. 1 times 6 plus 3 times 0.
Is that row 2 times column 2?
Let's see, did I mess up? 1
Oh, no, but
times 6 plus 3 times 0.
I mean, wasn't it
when you laid
Oh, I went to the wrong thing. Yeah, I did. That should be R1.
Oh,
Because we're still in row. Where are we in my just so you're confirming?
yeah,
Where in the solution matrix? Which row is this?
row 1.
So I accidentally put a 2 there.
Oh, I see it now. Okay, I see it now.
Yeah. So everything like these right here literally stand for the position in our solution, and they also tell us what to use up top.
Mhm.
Okay. So my bad on that. So now let me double check these row 2. Okay, good. So row 2, column 1, 2 times 4 plus 5 times 1. Always hurts my brain just enough, like just enough. 2 times 4, 5 times 1. Yep. 8 plus 5, 13. And lastly, row 2, column 2, 2 times 6 plus 5 times 0. 12. So if I just wanted to clean it up for us, 7, 6, 13, 12. Side note. This handy dandy calculator has a matrix set of tools right there. Actually has some vector tools too. I'm still learning all the things, and I'm actually curious now what they're on for vectors. Ooh, dot product, cross product, magnitudes. This thing's just defeats coming to class. All right, matrix. We need to edit matrix A. 2 columns, 2 rows. I feel like that is not. Why is it a 1 by 1? Oh. There we go. 1, 3, 2, 5. Four, 6, 1, 0. So if you missed what I did there, watch the video again. But you go into your matrix if you have this calculator, and you could use a calculator to do it. It takes a little time to set it up, but you edit the values given to you for A and for B, and then just go back onto your home screen. You go back to the matrix screen, literally under the names, take A and hit times B, and you'd be all set. Also, just because we're here, and I think I figured this out pretty quickly. Maybe I didn't. No? Okay. Guess I didn't. Made it worse. I'll just flip this over then. If you go to Desmos, but on their main screen, and you go into the math tools, they have a matrix calculator for you as well, which is pretty cool. Something relatively new. So you do something like new matrix. You can edit the rows here. I'm not going to use the examples. Do a new matrix. It uses capital B, 5, 2, and so on. And then A times B. And it would give you the answer there, which is not the answer. That's different because it's not what we had for A and B, but for times sake. So if you wanted to check your answer, obviously, you could do that using a calculator. You could also do your homework pretty quickly that way. But I think it's a good time to say that there will also be a non-calculator page on the next exam.
And on the final too.
Oh, definitely on the final. The non-calculator part on the final is going to be a little bit longer than what you did before. So we'll talk about the final after. So as long, like, it's worth seeing the technology, and it's worth knowing how to execute this still as if we were in 1500s. All right, give you a moment. Find B times A. Once again, proving this is not going to be commutative. I always want to say cumulative because it's that time of the year.
Professor, I noticed that on the calculator, it's a complex secondary observation thing. What is that?
I wish I knew. Let me give it a look, skis.
It's a clear off.
That's pretty sick. Not sure how to use that, but it probably. I like that they put that. They're smart how they design this. Okay. Oh, you can find the magnitude. Let's see, what is this going to be? 25 plus 4, 29 squared root of 29? Yeah, doesn't give the exact form.
Because you're in secret mode.
That won't matter.
So that won't matter. So
So square root of 29 is going to be that decimal. But it's not going to give you the exact form. There it is. All right. So that's what it gives you. Cool.
So that first row 1, column 1, that's 16.
Yeah, so this is row 1, column 1.
Yeah.
But this now is going to become our row 1. So we're doing 4 plus 1.
Oh, yeah. I did 4 times 1, and then I did 6 times 2, and I added them.
So I'm going to put it in the order I want. 4, 6, 1, 0 times 1, 3, 2, 5. So this is row 1, column 1. So 4 times 1 plus 6 times 2, 16. Yeah. And we'll stick with row 1, but we'll go to column 2. 12 plus 30, 42. And if you get to this point, you do not need to do this. If this helps you, you do what's helpful. But for this time in the class, this was an opportunity to see if you could do it. Row 2, column 1, 1 times 1, 2 times 0. Add those up. Take row 2, column 2, 1 times 3, plus 5 times 0 is 3. Did you get that? All right, so I want to, oh, sorry. So in general, we're going to find the dot product of the corresponding row with the corresponding column. Side note, I mentioned it really quickly at the last class. We only found the dot product of a vector that's 2, like a horizontal and a vertical component, and then a vector with another horizontal and vertical component. So we multiplied the horizontals, we multiplied the verticals, and added them together. But vectors actually really are used in 3-dimensional spaces. So you'd have a vertical, a horizontal, and like a height or positional, a z value, an x, y, and z value. And so the dot product extends. And if you extend your mind into maybe 4th dimensions or 5th dimensions, because mathematics can go into infinite dimensions, it just generalizes this position's product plus this position's product plus this position's product. So by calling this a dot product, it's truly what it is. And there is 100% a connection between matrices and vectors that we don't get to in this course. But some matrices are vectors, not all vectors are matrices, and things like that. So for us, just a little side note there, you're basically, or you are finding the dot product. So just to kind of work through a few things that I've said before, what's the order of our first matrix? Has 2 rows and 3 columns. And our second matrix has 3 rows and 1 column. So again, if these are in agreement, then this will be the dimension of your matrix, of your solution matrix. When I was in school, I used to do a little smiley face here and then say, yay. And if those aren't in agreement, there's literally no solution. So I need a 2 rows by 1 column. Row 1, column 1. Row 2, column 1. And we take everything in row 1 and find the dot product with all the corresponding positions in column 1. So 1 times 3, 2 times 4, -1 times 1, and add it all up. 1, 2, shoot. One, 2, -1 with 3, 4, 1. Multiply those, add. Multiply those, add. Multiply those, add. So 3 plus 8 plus -1 is 10. Yes. Five, 1, 3 times 3, 4, 1. 15 and 4 is 19, and 3 more would be 22. So that it's nice and clean. 10, 22. And if you think about it, if you're following this matrix multiplication and you know you need to do dot products, then it makes sense now why this has to be true. Like if we're finding dot products, everyone needs to pair with something, so those have to be in agreement. And then after you do those pairings, pretty much that's what's going to be left over. But if you don't need to know at that level. Just need to be able to execute it without a calculator. How are we feeling about that? So I can do another one, but getting the vibe, I think we're good. And if you want to stay after class to say, hey, can you go just talk one-on-one about it? I'm happy to. All right. Is there matrix division? Good question that we will answer. Starting with right now. So that's one section, and there'll be a homework there. So I'll answer it right now. Arguably, there's no such thing as division. Arguably, there isn't.
Can you explain on that?
Anything you can divide by is just multiplying by a reciprocal.
So,
Hence, we've come up with this actually. So please don't write this down. But in this class, we talk about inverse, right? Trig inverse, way back in like what? January, February. But we had multiplicative inverse. INV. I think the example used with us was 8, if I remember, when we were talking about inverse sine and inverse cosine. I was like, what is the multiplicative inverse of 8? It's 1/8. It's because if you take any number, fill it in here, anything you want, 5, and you multiply it by 8, then the undoing, which that's what inverse stands for, of multiplying by 8 is multiplying it by 1/8. And that goes down to like the what we call axiomatic level of mathematics. Like that's an act, like these are like what it is. This is like where we start in math. And in the axioms, the word division is not stated. So there is no such thing as division. That's a gray area, but in the hardcore math, like Bible level math here, it was stated on the top of a mountain that the multiplicated. No, okay, but right now there obviously there's division, right? We teach it because multiplying by 8, 1/8 is the same as dividing by 8. Right. Cool. I think that's cool because you literally asked, is there division, which led me on this little rant. And the next section is called inverse matrices. So we're getting there. I did not pay him to ask that question at that time. First, an identity matrix. Oh. Ones with down the main diagonal and zeros everywhere else. All right, so an identity matrix, first and foremost, is always a square matrix. Always a square matrix. And secondly, it has ones all the way down the main diagonal. So what is the main diagonal? It's the diagonal that starts in the first row, first column, and works downwards. And then there's zeros everywhere else. We use I sub n to represent the identity matrix, where n is the size of the square matrix. So for instance, I sub 2 is the identity matrix with 2 rows, 2 columns. Therefore, it has ones here and zeros everywhere else. And I sub 3 would be a square matrix that has 3 rows, 3 columns with ones down the main diagonal and zeros everywhere else. What's the identity in the real numbers from multiplication? So actually, yeah, let's answer that question. In terms of multiplication, what do we use to get back yourself, hence the word identity? What is the number that is the identity in real numbers? So 8 times what makes 8? 1. And that's what an identity is. So here in matrix world, 1, 5. Someone else give me a number.
7.
And I know that was crazy. 3. Why is this called the identity matrix? Just like the number 1 is called the multiplicative identity, then A times B gets us back the same thing. Hence the word identity matrix. That's why it's called the identity. When you multiply by it, it's like doing nothing.
But how is this used in matrices?
Okay, I'm getting there. So let's use 8 times the identity is 8. So matrix A times its identity equals itself. We'll keep that there for a minute. Well, how did we find the inverse? I'll just keep this right here. So if I do 8 times the multiplicative inverse, multiplicative, my spelling is way off. Take a week off from school. What do we get back? So what was the multiplicative inverse here? What do we get? You get back the identity. Furthermore, 1 over 8 was 8 to the negative 1. That's the same thing. And in function world, a function and its inverse has that notation. So in matrix world, A times its inverse has to give us 1, 1, so on, 0, 0, however many. Has to give you back the identity. And it kind of answers David's question, is there division? And the answer is no. But there is multiplying by an inverse, which would get you back to the identity, which is like undoing something. Okay, so everything that was kind of discussed so far. So before we actually get to it, if a square matrix has an inverse, so that's implying it's not going to, and I kind of say that at the end, we say it's an invertible matrix, but otherwise we call it singular. So before I tell you how we find whether or not a square matrix has a inverse, and if it does, what is it? Let's confirm that these two matrices are multiplicative inverses of each other. How would we do that?
We'll find the dot product.
Multiply.
Multiply, and what's the answer have to be?
The 1 0 0.
Has to be an identity. All right, so let's do this. Row 1, column 1, 2, -1, 2 plus -1, 1. Row 1, column 2, 1, -2, 1 plus -2. Not. Can't be. So did I set up a trap? Maybe. But it's not the inverse. All right. Would have to be a 0. But I am curious about one thing here. There was a typo. This should have been a 1, but that's okay. All right. So for time's sake, we learned something that, hey, no, it can't be. That would have had to been a 0. All right. So a quick method for finding the multiplicative. All right, so here's a fact. The way you find the inverse of this matrix is given by that. How did someone come up with this? I will use a word here, algebra. So we're not going to do this because it's way too painstaking algebra, but I'll give you the outline of it. So we're going to start with, hey, suppose we had A, B, C, D, and we don't know. So I'll say question mark number 1, question mark number 2, question mark number 3, question mark number 4, what this is, but I know it has to make 1, 0, 0, 1. And what we would do is a lot of called systems of equations, if you remember that, where you have like 2 variables and 2 unknowns. Well, we're going to have 4 variables and 4 unknowns. And so it's just a lot of algebra. But we would just say, let's set up a bunch of equations. I'm just going to do one of these and let it go. But we'd start saying, all right, A times question mark 1. First of all, I don't want to use question mark 1, but I'll call them W, X, Y, and Z. So that's my goal, is I'm really trying to figure out what this looks like not in W, X, Y's, and Z's, but in like using A, B, C's, and D's. So we would say AW plus BY equals 1. And then you set up your next equation, your next equation, your next equation, your next equation. And the goal is to eliminate every W, X, Y, and Z you see, so you only have A, B, C, and D in your answer. And if you did that, which I've had to do twice in my life, and it's doable, but it's a headache, you ultimately end up with this, each one of these, all divided by this. So we factor out this, and this is how that would generalize. So there's where this formula comes from. Literally using the fact and painstaking algebra. So this is a good memory must know for at least 1 week from now. The inverse of a 2 by 2 matrix is 1 divided by the determinant of the matrix. Okay, another word there, determinant. You take your main diagonal and subtract the other diagonal. So AD minus BC. And that becomes a scalar multiplier, 1 over that. So we're going to eventually distribute that throughout. And next, you interchange your main diagonal. So D becomes A and A becomes D, and you negate B and C. So few things to recognize there. Furthermore, why is it potential? Say this correctly. So does every square matrix have, or every 2 by 2 matrix have a inverse? No, because if this makes 0, then we're in trouble. Hence the word determinant, and hence why I said if there is a inverse, is not always an inverse. Is not always something that's going to work here.
So for the exam, we're going to have to like test out and make sure that the inverses are, of course, I know I didn't find it right in the solution.
What was your question?
Like, can you show us a problem
Yep.
where like the inverse will be like not a solution? So
It would just have to be
yeah.
A times D minus B times C. The determinant has to be 0.
Yeah, but can you give us like a big problem where it's not possible?
A big problem?
It's in like practice.
Yeah, that's what you need to do. Let's find the inverse of this. So I'm going to call this determinant of A for right now. Stop practicing this. So switch your main diagonal 1 and 3, and then negate those positions. So switch positions, negate positions. Next, the determinant of A. Also has that symbol. 3 times 1 minus -1 times -2. And that right there would be R, or the inverse of A. Let's do one. Whatever you tell me. Keep the numbers simple, but let's see where it goes. I need 4 numbers.
8.
Too big.
Oh. 3.
And -2
2.
and 1. Okay. Let's find this inverse.
What if it's the 8 for like a 4?
Nah. Then they're going to think we're in cahoots. It's up to you. Do you want to switch it to a 4 or keep it an 8?
You said it was big, so might as well.
I just didn't want you to go any larger.
Okay.
All right. B inverse is 1 over the determinant of B. So I wrote it in its formula form earlier. Then I used the word DETB, but now that's also how it's symbolized, right? So you should know all 3 of those. You also need to know switch positions, negate values. Oops. What's the determinant of B? 8 times 1, that product, minus this product, -6, which is